Right.
Okay, so then.
So we're recording.
Yeah. So this is Paolo, Perrone, and Markov categories.
Already sharing the screen, or should I do it? All right, can everybody see?
Yes, the slides are showing.
Okay, just a moment, because there's whatever. Sorry about this. All right, can you see now?
Yes.
All right. All right, sorry for the delay. Thank you all for coming. I'm going to talk about Markov categories, which are, since we were just talking about process theories, basically a way to do probability theory and treat it as a process theory. So we're category theorists. We like working with arrows. So we want to do probability theory from the point of view of processes, like imagine random processes, such as stochastic processes, or more generally from the point of view of like transitions that have some randomness. So I guess the best way to start is by a very concrete example. So imagine morphisms that have some randomness, such as this one. So you have two finite sets, and then you can transition from an element of the first set to one of the second set with some probability, okay? So now, these orange arrows are not the morphisms, okay? This is one morphism from the set A to the set X. Okay, so these are orange arrows. Imagine them as the maps to arrows. Except that instead of mapping one point to one point, they map one point to possibly many with probabilities. Okay? And same thing for every point. So from B, you can transition in this way. All right? So this object, well, this morphism is usually called a stochastic matrix because you can write it down as a matrix where you see the entries are non-negative reals, and the sums of each columns have to sum to 1, so that you can see those as probability measurements, okay? You might know that these matrices compose, as in, if you take the matrix product, then the resulting product is again stochastic. You can try to prove it if you've never done it. And the entries of the matrix, like these numbers, can be seen as conditional probabilities. So for example, you can view this 1/2, which would correspond to like, oh, what's going on? Alter, echt. Somebody is shutting down the system, and I don't know why. I didn't do anything. Are the people online still there?
You might not be able to hear their voice because...
Okay, they're writing in the chat. We still see your screen. All right.
Okay.
Yeah, thank you for your patience. It's just that the screen here has deactivated, at least one of them. I'll be right there in a moment. All right, so I was saying that, so you see this arrow here, for example, is, you can view this as a conditional probability. So the probability of ending up in Z if you start in B, okay? Now, okay, so we write it in this conditional probability notation. or transition if you prefer physical notation. All right, so this has to be a category. What's the composition of these guys? Well, all right, suppose you have another set and some transitions, then let's try to think of this in terms of probability. What's the probability of going from A all the way down to K? Well, you have to transition from A to, say, X with some probability, and then independently transition from X to K with some probability. And then you could have passed through Y or Z, and those are disjoint, so mutually exclusive. So you have to sum over all the intermediate steps, okay? So you have two independent probabilistic transitions, and you sum. This is called the Chapman-Kolmogorov formula. It's usually how you compose things in a Markov process. And you might also recognize that if these are just the entries of a matrix, thankfully, this is just the row by column product of matrices. So we can just use matrices to do our modeling here. Now, the states, we call states morphisms from the monoidal unit, or in this case, from the one-point set. What are those? Okay, those are probability measures, and that's how they enter. Because you see here, each column of the matrix can be seen as a probability measure on X, Y, Z. So for example, this blue one, this one here, is like saying that Y and Z both have probability 1/2, okay? So you can alternately, instead of viewing these as transitions, you can view these as probability measures if they are from the one-point set. And if you have a non-one-point set as the input, then it could be a family of probability measures. In this case, there's an orange one and a blue one. So a morphism can equivalently be seen as a parameterized family of states, a parameterized family of probability measures. And these two interpretations are both valid, and it's also helpful to pass from one to the other one. All right? Okay, so this is the simplest case, the finite case. Let's make this a bit more interesting. What happens if instead we want to do infinite continuous probability? Then the first problem we have is that, well, points now might have probability 0, but that doesn't mean that the probability is like really 0 in a neighborhood, right? So how do we do transitions in the continuous case? Instead of going from a point to a point, we have to go from a point to an event, to a measurable set. So the construction that we want is called a Markov kernel. What is a Markov kernel? So it's now a little bit asymmetric, as in it takes a point and the measurable subset. So we need to have as objects here measurable spaces. So space is equipped with a sigma algebra. And now we get a number, which is the probability, if you want, of ending up in A if we start in X. The condition that before was the column sum to 1 is that if in A here you take the whole thing, then this needs to be 1, so that in this argument we have a probability measure. And in the other argument, we have the technical condition that we want this to be measurable. So, and since everything is finite, it's equivalently saying it's integrable in the Lebesgue sense in the first argument. So we can integrate over it. Why? Well, because if we compose them, we have exactly the same formula as before, except now instead of a sum, there is an integral. And we want this to make sense, okay? So if you remember the Chapman-Kolmogorov, the one that was summing over intermediate states, now is integrating over all the intermediate states, all right? And this measurability condition and the fact that everything is bounded assures us that we don't run into any problems. So everything here works as nicely as it can. Oh, yes, very good. So yeah, you will find these slides on the website without these like pausing. So it's all there. You might need them if you then want to do the exercises. All right, so that category is called stock, okay? And it's the generalization of the previous one to the continuous case. Given a measurable function, we have a particular non-random transition, which just tell you that, okay, suppose that, for example, from X, you can just land in exactly this point, probability 1, right? That's a well-defined kernel, not very probabilistic, but you want to account for that. And so that gives you this kernel, which gives you probability 1 if your A includes where you land and 0 otherwise. And that's functorial, so that maps functions into kernels functorially. So from the category of measurable functions and to the category of Markov kernels. All right, so these are these two basic examples that you should keep in mind when we do Markov categories. These are two concrete ways of doing that. The simplest case of stochastic matrices and this more measured theoretic case. But it turns out that what you do categorically is kind of blind to which category you actually take, as long as the right axioms are satisfied. And so let's go to the general definition. What's a Markov category? So a Markov category is a symmetric monoidal category where, moreover, each object has two distinguished maps, which we call copy and delete or discard. And we write them in terms of string diagrams. So we read our string diagrams going upwards, like in physics. So this map goes from x to x tensor x, and this map goes from x to nothing, where nothing is the monoidal unit. And now we want these maps to equip our x with the structure of a commutative comonoid. So you all know what a commutative monoid is, right? It's associative, unital, and commutative. So if you read these from top to bottom, you see this is just a monoid. But we have to go up instead, all right? And the interpretation here is that these are copies and they are perfect copies. So let's look at co-associativity, for example. This tells us that if you copy and then copy one of the two copies, it's the same thing as copying the other copy, right? So in some sense, it tells you that these are perfect copies. You don't lose. You see, for example, this third one has been copied twice here and once here, but we haven't lost anything in the process. So the copies are perfect. Here, too, that's also a similar interpretation. It tells you that if you copy and discard one of the two, it's the same as doing nothing. So again, the copy process is lossless. And this one tells you, in some sense, that the two copies are the same. Like if you copy and switch them, you get exactly the same thing, all right? Of course, these are interpretations, but this kind of tells us this interpretation as in copying and discarding is consistent. Now, on top of this, we need the copies to be compatible with the tensor product. And here is an optional axiom that which we assume for simplicity. We want the category to be semi-Cartesian, as in the unit is the terminal object, or equivalently, applying a morphism and then discarding the result is the same thing as discarding the inputs to begin with, right? So in terms of information, this is rather intuitive. You might want that. In probability theory, this has to do with the fact that probability is sum to one. But you can also do, like, I want to say more measured theory where things don't sum to one. So you don't have to assume this to do categorical probability, but it simplifies a lot of things, right? Yes, there is a question.
Sorry, how do you interpret
this one? Oh, that's telling you that copying the tensor product of two objects is the same thing as copying both separately.
At the same tensor product diagrams.
Yes, the one that makes you, yes, the juxtaposition in the string. Yes, thank you. Oh yeah, feel free to interrupt me with any questions, especially here in the beginning. All right, so let's see what these copy maps look in our example. In Finstock, we have stochastic matrices. So what does it mean to copy X? Well, from X we go to XX, all right? And so we just copy whatever information we have. So you see it's something like a diagonal embedding. What I wrote here is a function. You might want a stochastic matrix. Well, I take the stochastic matrix that maps X to XX with probability 1 and the rest to 0 and so on, all right? What happens in the infinite case? It's, again, something like, okay, I've done it here for the unit interval. It's, again, some kind of diagonal embedding, but again, this is a function. How do you write this as a kernel? Well, I have to test for events, right? So x of x is in the event A in the first component and in the event B of the second component. How do we write this? Well, the pair x with the same x is in A times B, if and only if, well, x is in A, and x, the same x, is in B. So if x is in the intersection, in particular if the intersection is non-empty. And so this is the kernel. You can prove that's a well-defined Markov kernel, which is just the one, remember this functor from functions to kernels that takes the functions given by the diagonal embedding and gives you the kernel associated to it. All right. You might wonder, why do we want to copy? What's that good for? So in the next 2 or 3 concepts, we're going to use this and see what's the interpretation and why it has to do with probability and information theory. First of all, let's take a look at the discard map, because that also is a little bit counterintuitive. So discard maps alone are like a little bit hard to imagine, but discard maps together with other things are easy because they're sums and they let you form marginals. So probability theory is all about interactions. It's all about like even inference, right? It's not just about measure spaces, but it's about you have some randomness here and some randomness there, and somehow they're related. Maybe here it's a sequence and there it's the limit. Or maybe this is a certain process you're studying and there is some conclusion you can draw, and allows you to infer one random thing from another one. And in some sense, the discard map lets us go from the whole to a part of the system by discarding the rest. So suppose here I have two states, so two probability measures, one on X and one on Y, which let's say in Finstock, so you can draw them this way. And you can form the product probability on the whole thing. The colors will make sense in a moment. We write this just as a tensor product. We say that this joint distribution R, so joint distribution means that has more than one output, is just a product of these two. Okay? Now, in a situation like this, we say that we can split this R into just these two parts. So the whole is just the sum of its parts. And that is related to the fact that if here that we have some randomness, but for whatever reason we know that we are in this orange situation, does that tell us anything about X? No, still anything can happen, you see? So knowing something about one output doesn't tell us anything about the other output. And so these can be like split. But in general, there are measures like this one, I imagine it renormalized, of course, where you see that one is not just a product, okay? So it's still true though that you see if you project this down to here and this down to here, you still get P and Q. So we write it like this. So you have R and discard Y, you get a state over X, which is P. In Finstock, that corresponds to, you have a probability with two entries and you sum over the Y's and you just get P of X, all right? So that's the marginal probability. Yes, David?
So discard.
Yes.
Can
Oh,
slides?
everywhere.
You use it it's not just for.
In this talk, I use it everywhere.
Okay.
Because a lot of things I can say, like, if you don't assume that the monodic unit is terminal, you can still say stuff kind of like this, except that the statements get a bit more complicated. There's a bit more bookkeeping. But there is one specific situation where this just does not happen, which is in, I guess, the first exercise that we're going to have. There, it really works only if you have a terminal unit. Maybe I'll tell you there. Thanks for the question. Okay, so here, so you see, what's the discard map? Alone, it's hard to say. But here, it's basically summing over this. Summing over something, marginalizing, discarding, averaging over that. So that's the thing that takes you from a joint distribution to a marginal distribution. Imagine the projections, okay? And now you say that in this situation where this is not splittable, then knowing that we are in this orange situation here does tell you something about X. Y is random, X is random. However, if you know Y, then you can, in this case, limit your choices, or at least modify your choices. Like observing Y in some sense can give you some information about X, okay? So yeah, that's not in the sense that X depends on Y as a function or as a morphism. I want to say not yet. But it depends in the sense of stochastic dependence. So in the sense that you can do some inference and kind of run the diagram in this U direction, okay? Let's make this a bit more precise. We say that a joint state here exhibits independence of X and Y if and only if it is the product of its marginals, okay? You can show in the exercise, you'll see that that's exactly saying that it splits. And this is a thing that just works if we have the monoidal unit terminal. If not, things are significantly different in that case. We have a one-way implication. But in Finstock, so in traditional like discrete probability theory, that's when you say the probability is the product of the probabilities, like independent coin flips. Okay? You write this like this, and that has to say like you can split this into two. And again, splitting meaning that X cannot tell us anything about Y cannot tell us anything about X. The first coin will not tell us anything about the second coin, right? They're independent. All right. More interestingly, and now we're finally seeing the copy map. If we have some inputs, we say that this should not, oh, there's some typos here. This H should be P, sorry about that, and this X should be a Y. But I hope it's clear anyway. So this P exhibits conditional independence of X and Y given the inputs. Okay, if and only if this is true where we copy A. So let's try to interpret this. First of all, in Finstock, this is the same equation as before, except that everything depends on A. So where does the copy map come in? Well, because you see here, this is the same A. It's not A and A prime. And so we need to copy the same value here and feed it into both. So if you want to be careful, then you have to put the same A there and use the copy map. We can also say, what does this tell us? Well, that's kind of telling us that it might still be that knowing X tells us something about Y. No. However, it doesn't tell us anything more than A does. So if you know the input, then knowing one of the outputs will not give you any additional information about the other output, okay? So you can say something about X if you know Y, but if you know A, then X has nothing more than that, right? And you can see it here. You can view it topologically, like the knowledge from X to Y kind of passes through A, factors through A. If you know the theory of like probabilistic graphical models, that might remind you of like Markov random fields or Bayesian networks, and that's exactly what it is. Markov categories actually give you a version of Bayesian networks, like if you use Stern diagrams. So the important thing is that you see X and Y might be related, but given A, they are not. If you're not familiar with this from point of view of statistics, let me give you a very concrete example, all right? Here are two things that I like a lot, pizza and espresso, and this might be some data that you take from people about how often they have pizza and how often they have espresso. I am this point here. And you would say, all right, that's X is pizza, say Y is espresso, and clearly there's some correlation here. So knowing X will make you do some nice prediction about Y. Like if somebody has a lot of pizza, it's likely that they will have a lot of espresso too, right? If you don't know anything else. Suppose, however, that you take the data, like that your data come from this data set. So this part of the data are people from Italy, like me, remember I'm here. And Italians tend to have a lot of pizza and a lot of espresso, but you see in there's no correlation. It's basically a circle. So once you know you're Italian, you know you'll have a lot of pizza and a lot of espresso, but it's not that the more pizzas you eat, the more espressos you eat, okay? And the rest of the data is taken from the rest of the world, like very biased data towards Italy, just for the sake of the argument, okay? And again, also here, you don't see any particular correlation. Like people that are not from Italy will tend to have less pizza and less espresso, but it's not like the more they have pizza, the more they have, okay? These are not real data. I guess pizza is a lot more popular than espresso, so I guess everything should be skewed to the right. But now you see now that if this is your data set, then if you don't know where people are from, then it's true that knowing the pizza frequency tells you something about the espresso. But if you know the input, if you know where these people are from, then knowing if they are having a lot of pizza is not going to tell you anything about their consumption of espresso. Nothing that you would not know already by just knowing where they are from, okay? So in statistics, you usually say that, in this case, variable A, where you're from, explains away the correlation, right? So usually, if there's some randomness, it might be that knowing something about X tells you something about Y. So X has some hidden information about Y. But this information is fully included in where they're from. If you know where they're from, there's no extra hidden information in that correlation. All right? Now, is this clear for everyone? Because this will be crucial in the rest of the talk. And this is like one of the places where Markov categories really shine. So before we go on, any questions or anything not clear? Okay. So it's important here that if K is probability of eating a lot of pizza and AH of espresso, then you need to test them on the same person. That's why you're copying here, okay? So these are the X and Y coordinates of the same point. And that's where the copy maps come in. All right, now, next, determinism, and that's another great motivation for why. Morphisms have randomness. What does it mean? Well, it turns out that it's hard to say what it means when something is random, but it's a lot easier to say when something is not random. And some morphisms will not be random. So we say F is deterministic. F and copy the output. Copy the input and feed it. Down, you see that that's exactly the same. F is a morphism of monoid. All right, so suppose, for example, that F is this function, takes an integer, and flips a coin. If it heads, it adds 2, and if it's tails, right, so let's try it on both things. So start say with 2 by F. So with probability 1/2 we end up in 4, and probability 1/2 will end up in 5. I'll get to the end.
Your
of
microphone might have turned off, I think.
Can you hear me now better? Is this better? Yeah, okay. Since when did you lose me? Before flipping the coin. Flipping the coin like in this slide? Yes, all right, all right. Now I can use next. Okay, so I'm saying, suppose that n is this function that flips a coin and adds 2 if it's heads and 3 if it's tails, all right? Like, now, let's start with 2 as an input, but you can do any number. So if you apply f, you get 4 with probability 1/2 and 5 with probability 1/2, right? And now you copy the result. And you see that you might get either 4, 4, or 5, 5 with probability 1/2 and 1/2. You don't know which one, but you know that they're going to be equal, okay? You have perfect correlation here. In the second case, let's say you start again given like with 2, you copy it, so you get 2, 2, which is, you know, a point out of a plane of values. And now you apply f to both components separately. So you see the first one might be 4 or 5, the second one might be 4 or 5, but there is some possibility that the two things are different. So you get 2 different distributions on y times y, 2 different kernels, 2 different random things, okay? So in the second case, these things are fully independent. Well, conditionally independent given the input. So basically, you can view determinism as saying that this map here, f and then copy is the one giving you perfect correlation, is splittable in the sense we said before, if and only if this thing is deterministic. So I like here to quote Einstein that famously said, madness is doing the same thing twice and expecting different results. Now, don't know about that, but that more than madness, that to me is a perfect definition of randomness. That's exactly what it is. You do the same thing twice and you get different results. And that's the definition we're using here. Okay? Now, Einstein said that in the context of quantum mechanics because he didn't like the fact that quantum mechanics had randomness. Here, it's all classical, but we can kind of recycle the same idea. Like this up here looks a little bit like entanglement and so on, but this is not quantum, this is all classical. But that's the idea. You do the same thing twice, and it's different. Okay? Okay, no more questions. Very good. And for states, the copy map of inputs is trivial, so it just looks like this. And let's see, all right. Does this determinism recover the usual notions of determinism? It turns out it does. So in Finstock, so stochastic matrix, a matrix is deterministic if and only if its entries are only zeros and ones. So you are perfectly certain about which transition is going to happen, everything else is zero. So those are the ones that come from like functions. In stock, similarly, you are perfectly certain about in which events you're going to land and in which you're not going to land. There's no 50-50 situations, all right? And this is one of the things you're going to have to prove later, all right? It's even better, but it's a bit harder to prove, so it's not in the exercises that in Borel stock, the deterministic morphisms are exactly those in the image of this functor from measurable functions to kernel. So the ones that, the only deterministic ones are really the functions in the nice case. But that's a bit hard to do, though, so it requires quite some measure theory. So it's not going to be in the exercises. All right. Any questions? Online. All right. So here are some. Sorry, I said this already. Oh yes. So let me say this more precisely, since it's going to be said later. So we can take the subcategory of stock given by Borel stock, where the objects are just, I want to say, the nice measurable spaces. So like R, which is also the same as Rn and the unit interval as measurable spaces, and like the finite and countable ones with the discrete sigma algebras. That's the usual stuff you use in probability theory because they're very nicely behaved, and in this case, the deterministic morphisms are exactly the one coming from this functor K. Okay? All right. Last thing I want to say before a break, proposition, a Markov category has only deterministic morphism if and only if the copy maps are a natural transformation, so everything commutes with copying, if and only if the monoidal product is the Cartesian product, and the monoidal unit is terminal, but we know that already. So what's going on here? I like saying that Markov categories are basically Cartesian categories where you turn on the randomness. Of course, that's not a mathematically rigorous statement, but it's very close to a mathematically rigorous statement, which says that, conversely, a Cartesian category is exactly a Markov category where everything is deterministic. And that's exactly this proposition, all right? Again, you'll see this in the exercises, but let's try to understand why this is the case. So if we have a Cartesian monoidal category, the product is the one, the categorical one that satisfies this universal property, okay? And in particular, it satisfies the universal property if A is the monoidal unit, and so you just have states here. But you saw before that given two probability measures here, there's many possible joint distribution on the product that project down to those. And that can tell you different things. So for this one, see, knowing we're in this orange element tells you that we're on the right side of X, but there could be another joint where knowing this tells us we're on the left side of X. And the fact that we have a whole choice of things there tells us that in general, there's different things that we can, the different, like, let me say, information flow between X and Y. There's not just one way from going to one to the other, which means that it's possible to like try to infer this information. okay? But that also tells us that we have existence, but not uniqueness for this map, okay? So in some sense, the fact that there's correlation is an inevitable fact about randomness. And conversely, we also saw that randomness is what makes correlation possible, okay? That's kind of what our proposition is saying. If you turn off the randomness, then there's also no choice here. So it's a little bit like in information theory where like entropy and mutual information are like special cases of one another. Like, but I guess I'll talk about it in the next few days. Yes, there's a question?
Saying that if you start with a Markov category, apply some functors to the morphisms like max rather than the probability, end up with all of them being category would be a Cartesian category.
No, not quite, because you're thinking about the 0-1 thing, right? No. That's not true for every Markov category, but just for like stock and finstock. So in a general Markov category, you don't have this 0-1 thing. So if you have the category, say, of like sets and like relations, in that case, the deterministic morphisms are those that map an element to only one element and not an entire set.
Maybe I'm asking is there a consistent way of removing the randomness from a Markov category? Back to Cartesian category out the other end.
In some sense, yes, but in a disappointing way. Like you can just restrict to the deterministic morphisms, but I'm not aware of any, for example, a join to that. Like you can do that if you change the codomain, but not with the same codomain, like to just turn off the randomness functorially, not as far as I'm aware. But there is an adjoint there in the sense of probability monads, so we'll do that like later in this tutorial. Maybe that answers your question. Yes? Yes? Yes. Yes. Okay. So yeah, what I wanted to say then you see that the fact that things can be correlated is equivalent in some sense to the fact that things are random. So randomness allows you to have this inference thing in a meaningful way. And if you don't have one, you don't have the other one. So in some sense, remember that it was about like your randomness allows you to like infer an output from another output. But suppose that your outputs depend deterministically on the input. Well, then if you know the input, you know everything. So there's nothing that one output has on you that the input wouldn't have given you already, because knowing the input, you know exactly what's going to happen with probability 1. And that's kind of what's happening here, okay? All right, so time to stop. There's some exercises. There's a few here and a few that you can download from the website, where there's a few more in case you finish these sooner. Okay, so you're welcome to look at these. And if you finish these, either help your neighbor, that's how collaborations are started usually, or look for more difficult ones on the website. So the first one, as we said, and this is the one where you really need the monadal unit to be terminal, that if something can be split, like decomposes as a product in this way, then the factors are the marginals. Like it decomposes as the product of the marginals out of all the things. The second one is to show exactly that the deterministic morphisms of Finstock are the matrices with these entries. Once you see what to do, it's not so hard. It's a little bit harder in the measured theoretic case. So for those of you that are comfortable with like measurable spaces, try also to do this in the continuous case. Third exercise, prove this proposition that we just said. And if you want a hint, use the fact that, which you also have to prove, that a morphism is, if a morphism with two outputs is deterministic, well, in both outputs jointly, then it is always make them conditionally independent, which is kind of what we said, right? There's no room for wiggling interactions if everything depends on the input strictly. There's nothing X can tell you about Y if Y only depends deterministically on A. Try to prove that in a Markov category, and that should help you with the difficult direction in this proposition. All right? So We have about 10 minutes before the coffee break. What I would do is start now, then we can have half an hour of coffee break. So of course you're welcome to ask me more questions during that. And then after the coffee break, we'll have 10 more minutes again for these exercises. So the teaching part of the tutorial will start at 4:10, okay? With the coffee break in between. What should I do? Should I pause the recording or? All right, I'm gonna pause the recording. I really hope I remember to unpause it later. All right. And as I said, there's more exercises on the website, so if you want to. Yeah, we should ask Owen for the precise link, I guess, or. Oh, thank you.
Oh, yeah, it's the conference. Oh, okay, all right.
Yeah, it's in the conference website.
Yeah, it's the conference. Oh, okay, all right.
Yeah, it's in the conference website. Oh, that's why. Oh, okay. Can you hear me now? Yes. Okay, so maybe let me start from here. We said that whenever things are interacting, so whenever you cannot split this joint, then you have the situation where knowing something about y can tell you something about x, and the other way around, okay? But we also say that that doesn't mean that y is an input for x. It's like that you're kind of walking this diagram as a U-shaped thing. Now, there are some nice Markov categories where you can turn this inference process into an actual morphism. So where you can find, in this case, let's say we want to go from x to y. And so what does it mean that we have a conditional? So this reasoning that x has an influence on y, like has an influence on our knowledge of y, can be made as a dependence from x to y, of course, usually involving some randomness, because we don't know that x and y are perfectly correlated, right? In general, they're not. But there's a morphism from here to here that kind of captures this idea of this information about y that was encoded in x, since they were correlated, okay? Of course, if this is splittable, you can still do this. It's just not particularly interesting. Because remember, when this is splittable, then this does not really depend on this, so you get something that's constant or almost surely constant, okay? So I hope it's clear what we want to do. We want to turn this inference into an actual morphism. Okay, so here's the formal definition. A conditional distribution of P, in this case given x, but of course you can also do it the other way around, is a morphism that you write like this from x to y, usually random, such that this joint is the same thing as you just take the distribution over the first element and marginalize here, so discard the other guy, keep your x, and regenerate y using your newfound morphism. So you see that now this time, this way of going from x to y with a U shape is exactly that. X is always the same here, and you reconstruct y using this morphism. So this corresponds in Finstock to saying that the joint is the marginal times the conditional. Bayes formula in some sense, if you want. Is this clear? The question? Yeah? In some cases you can, like you can talk about like conditional expectations. That can be done categorically, but to do it nicely, we're still working on it. So we think one can, and there's like a universal property there, but we still are figuring out like the details. But so in traditional probability you can, and we think that can be made categorically quite nicely. I put an asterisk here because this morphism is defined only up to almost sure equality, and in an exercise you're going to have to show that. All right, now, when do these exist? So in Finstock, you always have this, okay? And the reason is that for all the points that don't have zero probability, like you can divide. You can try to even prove it yourself if you want. It's not too hard. What is hard, though, is to prove that they also always exist in Borel-Stock. And to do that, you have to like use the Radon-Nikodym theorem and do some actually non-trivial things. Okay, but so the fact that for nice probability, nice measurable spaces, all conditionals exists is one of the reasons why you want to do probability in that category. Like traditionally, when people do probability theory, they do it in standard Borel spaces. So here I said classical probability theory in quotes, because I don't mean classical as in not quantum, I mean classical as in not categorical, okay? So they usually work in this category, and this is one of the main reasons you have all conditionals. You don't have to worry about them existing. In general stock, this might fail to exist, okay? You can still talk about conditional probabilities using like conditional expectations, but they don't assemble nicely into an entire morphism or kernel. So basically, you can still talk about this inference process this way, but it doesn't become a morphism, like here. But in Borel-Stock, it does. Yes, there's a question?
In the Finstock and Borel-Stock cases where it always exists, and you said
That's true. It's going to be part of the exercise.
My question, because it seems it's a bit like in the categorical quantum setting where you might compose with a cap to turn a map from.
Yes, it's very similar. Maybe it's even inspired by the quantum ideas. I mean, this was first defined by Bart Jacobs, as far as I know. I don't know if you had quantum things in mind, but he did work on them. There's a little difference with the quantum in that there's no cap, just a cup, and that in general you don't have a uniform distribution. So, like you don't have the dot from below, basically. But yeah, but it's analogous. Like it's turning some horizontal reasoning into vertical, a little bit like you do with like a compact closed category. It's just a part of it though. Like it's just a monoid part. Well, comonoid. All right. Now, let's look at the most important example of conditioning, which is Bayesian inverses. So instead of a generic joint distribution in this form, we take this one, which is a joint distribution, has monoidal unit as input and two outputs. And we now condition with respect to y. So we plug in everything, and you see that the conditioning will satisfy this property here. Try to convince yourself that this is just an instance of this here, where P now is this. And we have flipped the order, okay? What does this diagram tell us? Well, that's telling us pretty much Bayes' formula. So probability of x and then conditional given x is equal to the joint, which is probability of y, probability given y. That's Bayes' formula, okay? So in terms of strain diagrams, you write it like this, and it holds in general. For example, in Borel-Stoch. So this one that makes very nice intuitive sense in the discrete case can be written in this more general form that has the same interpretation, okay? So in particular, if you have a transition from x to y, that f, then you also have one from y to x, given by conditioning. We will see very soon that in some cases this gives us a Dagger category. Okay, any questions until here? All right, now let's move on. How do I? Ah, there we go. So we're now going to talk about this construction, which is the Probstock construction, which is a new category constructed from a Markov category. One way to interpret it is a category where morphisms are probability spaces, so not measurable spaces, but with a probability measure, like measure spaces, and transfer plans. Let's do that. So given a Markov category that has all conditional distributions, like Finstock, like Borel-Stoch, unlike Stoch, the category Probstock has as objects pairs, where now the pair has an object of C and a state on it. So imagine a space with a probability measure on it, which is kind of like your basic measure, like fundamental measure on it. You can put other ones, but this one is always your reference. As morphism, oh, now let's be a bit careful because it's a little bit long. So we would like to take, first of all, morphisms of C, which preserve the measure. So such that if you apply the morphism to the old measure, you get the new measure. So something like measure preserving functions, or more generally, measure preserving kernels. But we take them only up to P almost sure equality. And that's really where we use P, why we need to keep that reference measure. So we identify any two morphisms if they're equal almost surely. Okay? In some sense, you can view your objects as like having some mass that they need to move. And these morphisms as ways to like move that mass, possibly like splitting it if they have some randomness. But we don't really care where they move the zero mass, like where they move points that don't have actually any mass. Okay, that's kind of the idea. We only care about the mass, not about points of the underlying space. We're not moving points, we're moving probability, so to say. We're moving measure. All right. Here's a theorem. Probstock is a dagger category with a dagger given by a Bayesian inversion. Now, I know it might be that some of you don't know what a dagger category is. So here's the idea. So first of all, you see that by doing Bayesian inversion using Bayes' formula, just like with P, we can go from, with F, we can go from X and P to Y and Q. Using the Bayesian inverse, we can go from Y and Q to P and X. Okay? Now, what this is telling us is that this is functorial and it respects the tensor product. So let's make this precise. What is a dagger category? In my opinion, one way of describing dagger categories, they're like, a dagger category is to a category as a directed graph is to an undirected graph, in some sense. What's an undirected graph? It's a graph where if there's an edge from X to Y, then you can also walk it the other way, okay? But that doesn't mean that the 2 points are the same point, okay? It just means that they're connected. And here it's kind of the same thing. So we have X and Y, and whenever there's a morphism from X to Y, there's also one from Y to X, but that doesn't mean that these two objects are isomorphic. Nobody's telling us that F dagger is the inverse of F, okay? But there's even more. So this is since now in a category you have multiple morphisms between any two objects in general, this choice of going backward for each morphism can be made functorial. And that's indeed the case. So if you take the Bayesian inverse of the composition of kernels, then almost surely, in the categorical sense, this is just the composition of the Bayesian inverses, okay? And so we can kind of view our morphisms that in some sense transport the mass equivalently as transporting the mass backwards, back to our space, and these two things encode the same information, okay? Yet another way to look at this is to consider the category of couplings. So to consider a morphism as coupling. So instead of saying that a morphism is just an almost sure equivalence class of measure preserving kernels, or, well, what was in the previous slide, equivalently, you can view morphisms as just joint distributions which restrict to P and Q as marginals. All right? Okay, any questions? If not, it's time for some more exercises. So I guess this time we can go until 35. And all right, so again, there's more exercises on the sheet that you can download. Here are the main ones. First one is to show that in Finstock and Borel-Stock, as we say, the P almost sure equality in the categorical sense is exactly the same thing as differing only up to a measure zero set that you do in probability. For Finstock, it doesn't require knowledge of measure theory. You can try yourself. For Borel-Stock, there is a little bit of measure theory that you have to use. So, I mean, if you don't know measure theory, well, do it for Finstock. It's still enlightening if you figure that out. Second one is, well, what we were saying before. Suppose that a conditional distribution exists. Then any other morphism is also a conditional distribution, if and only if is P almost surely equal to this one. Okay? So conditionals are unique only up to P almost sure equality. Another one you can try, so Bart Jacobs and Kento Cho have defined this equality strengthening, which is like a rather stronger property than almost sure equality. But if you have conditionals, it's equivalent. So try to show that if F and G are P almost surely equal for a marginal, then the stronger condition involving the joint is true. Mainly, it's kind of telling us that if we add information to our setting, these things stay equal. Okay, from here to here, you can do by discarding E, but the implication goes both ways if you have conditionals. And if you do that, then use this to show that prop stock is well defined as a category. The composition respects almost sure equality. So it's well defined between equivalence classes. Okay? So we have a little bit more than 5 minutes. Let's try, and then we will resume with the theory. Okay, I guess we can restart. By the way, if you wonder if there's solutions, so at the end of the PDF of the exercises, there's a list of papers. All the statements or very closely related statements are proven in the papers in there. If you need like more specific pointers than that, of course, feel free to reach out to me, okay? Okay, let's move on and talk about probability monads. So take now a Cartesian monoidal category. That, remember, that means no randomness. Say set, or measurable spaces and measurable maps. And sometimes the randomness can be encoded by a monad. So if you do theoretical computer science, you might know this very well. Take a monad, which is affine, meaning that it preserves the monoidal unit. The idea is the monad is taking a space and giving you probability measures on your space, and there's only one probability measure on the 1-point set. That with probability 1. And monoidal, or equivalently strong and commutative, which basically means that you have a map from the product of the probabilities to the probability of the products that intuitively forms the product measure. Remember this independence thing? And this needs to satisfy the usual associativity and unitality conditions. If you have this, well, then the Kleisli category of the monad is canonically a Markov category with the copy and discard map induced by the ones of D, except that now, usually you have interesting randomness. Like all the new morphisms that you got are not going to be deterministic in general. Okay? The prime example of this is that stock is the Kleisli category of the famous Giri monad. And sometimes people restrict, so the Giri monad restricts to Borel spaces, and that's how you get Borel stock. So both stock and Borel stocks are Kleisli categories, and the monad you use is the Giri monad. It's one of the things you can prove later. Finstock, I want to say it's almost the Kleisli category of the distribution monad. The reason why it's not exactly the Kleisli category of the distribution monad is that the objects of Finstock are finite sets. And the distributions over a finite set, even just the 2-element sets, are an infinite set. So that wouldn't work. But what is true is that Finstock is a full subcategory of the Kleisli category of the distribution monad. Okay? And there's not much more that you have to add to get the whole thing. So you might have heard about probability monads. They are related to Markov category in this way. Yeah, there's a question? Oh, yeah, that's a good question. Let me repeat for the online people. Elena's asking if there are conditions on the monads assuring the existence of conditionals. Not as far as we know, but there might be. We do have conditions on the monad that assures properties that are a little bit weaker than the existence of conditional, the so-called like positivity, for example. But as far as we know, we still don't have a characterization that gives us all conditionals. That's a really good question. We wonder too. Any more questions? Okay. Let's now look at the universal property. So from the Kleisli adjunction, or if you want from the definition of Kleisli morphism, right? Kleisli morphism from A to B is a morphism from A to PB. So you have a bijection like this. Now let's apply the unit dilemma so we feel like real category theorists. So take A to be PB and take the identity. You get the co-unit of the adjunction, which is a map from PB to B random, okay? Kleisli category. We call this map the sample map. So if you know probabilistic programming, you already know what this map is. If not, I want to say this is the map that in some sense generates all the randomness, right? Because by the universal property of this adjunction, every morphism in here is just this map composed with something that comes from here, like something that is deterministic. So all the randomness, if you want, comes from this map, universally so. What does this do? Well, it takes a distribution on B or on X, and it gives you a random element of X, but random following which law? Following which distribution? Well, the one you have here, okay? So it takes a distribution and gives you a random element distributed according to that. You use this all the time, say in basic probability theory, like year one mathematics probability theory. Sometimes you look at, for example, Bernoulli, like flipping a coin with bias P. What's that? That's a random variable that gives you 1 with probability P and 0 with probability 1 minus P. What is that? Well, what is P? P lives in the interval 0, 1, which up to isomorphism is the probabilities over the two element set 0 and 1. And the map gives you either 0 or 1 according to this probability. Okay, so you're sampling. So from knowing exactly what the distribution is, you go to not knowing what the point is, but of course you follow that distribution, okay? It's also what you do, I don't know, in Python or any other programming language, when you say generate a random number from 0 to 1. I mean, of course, ideally, like you give it a distribution, usually the uniform one, and it gives you a random number sample from that distribution, okay? And in case you wonder what the monoidal unit is, well, again, unit dilemma the other way, that gives you the Dirac delta. So it's a map from A to PA, that given a point gives you the probability measure that's just that point, basically, and 0 everywhere else, okay? All right. Let's say something more. So far, we've talked about marginals and joins between a finite number, usually a product of states. But of course, probability theory is way more than that. There's a whole theory of stochastic process and of limiting things that involve infinitely many random variables, usually arranged in a sequence, if not more, like you even have continuous times, but we're not going to do continuous times. How do we deal with that? Because we've talked about finite products. So we said that in the interesting case, those are not Cartesian, they're just monoidal. But what is an infinite monoidal product, right? We know what an infinite Cartesian product is, just a categorical product. And we know what a monoidal category is, but those has just finitely many factors. How do you do infinites? Here is how you do them. So for finite sets, we know how to form the finite product. It's this one, right? Just take n times the usual tensor product. If you have a subset, then there is a morphism the other way. So from the big product to the small product, which just discards whatever is not in that set. You see this picture? This is a like n-fold product. This has less elements, fewer elements. You just discard all the ones that are not in F prime. Okay, it's like a marginalization. Now, well, if you take an infinite set, you can form the diagram formed by all its finite products, okay? And marginalization is going to be a co-filter diagram. And now you take the limit of that. So usually, every infinite product is a co-filter limit of finite products. And so here we're taking a co-filtered limit of finite monoidal products, okay? So in some sense, the finitary part is just the usual monoidal product, and from finite to infinite, we actually use a universal property. That will not make this a categorical product, huh? Because this one in here is not Cartesian. But it's still a limit, okay? We need to satisfy some conditions, I'll be there in a moment, which are that it's preserved by the tensor product, just like usual products, because limits are preserved by limits, but we need to enforce that here, and that the projection arrows from infinite to finite are deterministic. There's a question? Oh, you can do both. You can take a filtration or you can form a filter. So there's a caveat. If you take I countable, there's no difference. If you take, no, But if you take I uncountable, then you cannot do it sequentially. But if it's countable, then it's fine because you can form a sequence that's going to be like cofinal in there. So there's not going to be any difference. Like you can also decide to walk just one chain in this diagram and it's going to have the same limit. So there's no problem. No problem. Yeah, that's a good question. So yeah, for those that know probability theory and know what a filtration is, this is exactly a filtration. Okay. The theorem is that in Borel stock, these always exist. So that's called the Kolmogorov extension theorem sometimes. It is a categorical statement that was stated before category theory. So Kolmogorov did this in the 30s, and category theories only appeared 10 years later. So it's a universal property pretty much ante litteram, like before it was called that way. So that also answers the question, why didn't Kolmogorov use category theory to use this? Well, because it did not exist. All right. I want to say that this theorem is about saying that, remember, it's all about interactions and correlations between finite products. I'm saying that those are just a finite thing. It doesn't happen in the infinite case. Let me try to make this precise. No products. So remember, we have this situation where we don't have categorical products, which means that, remember the situation before? In terms of the monad, you can see that as the fact that the monad does not preserve products. So the canonical comparison morphism from the functor of the limit to the limit of the functor is not an isomorphism. But there always is a map here by the universal property of this product, but it's not an isomorphism. So it's saying that the P does not preserve functors. If you've read 7 sketches, that's like P has emergent properties. So, however, let's now go from the infinite product. This is the Cartesian product now. So it's from the P of the infinite Cartesian product to the Cartesian product of the P's. Again, there's a comparison functor. However, we can write an infinite product as a limit of finite products. And so we can break this functor into two. First, we take the limit out of the functor, and then we take also the product, the finite products out of the functor. Okay? And now we know that the second arrow is not an isomorphism because this is the limit of arrows as in up here, like forming probabilities of finite factors, so factors of probabilities. We know since there's correlation, these two things, this is not an isomorphism. However, the Kolmogorov extension theorem is saying exactly that this is an isomorphism. P preserves those cofilter limits. So in some sense, it's true the stuff interacts finitarily, but not infinitarily. So an infinite amount, countable, of factors has only finitely arbitrarily large interactions. But going from finite to infinite doesn't add you anything else. Okay, there's no such thing as infinitary, I don't know, mutual information or correlation. All the correlations are finitary, arbitrarily large. A little bit like a finitary, say, Lauvier theory, finitary monad, contains only operations with finitely many terms, as many as you want, right? You have groups, you can multiply like 1,000,000 elements in a group, you can, but not infinitely many. And it's kind of the same idea here, okay? There's a question?
That P just preserves those specific?
Yeah, that's a good question. Let me repeat for the online people. Does P preserve all further cofilter limit or just this one? So the Kolmogorov theorem says specifically this one and closely related ones. I personally strongly suspect that it preserves a lot more, maybe all of them, or at least all those that exist. But I don't have a categorical proof yet. Yes, there's another question.
Does that make P a continuous?
No, because P does not preserve product. You see, it only preserves these particular limits. All right, let's pause here again. So we do 5 minutes of exercises and then we're going to have a conclusion. First one, well, prove that the Kleisli category of probability monads is a Markov category. Second one, if you know measure theory, prove that stock is the Kleisli category of the Jury monad. Third one, that's quite nice. Prove that sampling from a product distribution is the same thing as sampling from the factors independently. And this tells you why the product probability exactly encodes independent events. It's not an arbitrary choice that's just nice for the calculations. It's really the same thing once you sample. Okay, so there's a reason why you take the product when things are independent, and this is the reason. Like, it's another nice conceptual thing that you can see in terms of Markov categories. And last one, prove that the Kolmogorov product is the Cartesian product in the subcategory of deterministic morphisms. I don't expect that we'll solve it here now, because it's a little bit long, but conceptually, I hope it makes sense. Okay? So let's make another exercise break, and then, like the last 5 minutes, I guess, we'll do a little conclusion. All right. Any of you, of course, I'm sure no one has finished the exercises, but if you still have questions about them in the next few days, I'll be at the conference for free. All right, conclusion. This one is not going to be exercised. It's just a nice conclusion, because so far you're like, okay, you told us a lot of the definitions. What do you do with all these objects? Like, show us some actual probability theory. That's what I'm going to do. All right. You can prove De Finetti's theorem categorically using Markov categories. De Finetti's theorem is an old result from 1927, so it's almost 100 years old, like 96 years old. However, you still have, if you are subscribed to the probability archive, you still have people coming up with new proofs of De Finetti. Like, they're not satisfied with the proof. Not that they're wrong, of course they're right. But to us as humans, they don't always tell you what's going on, or at least not to every mindset of people. So we made this worse by giving one more proof, right? No, so we gave a categorical one, which we believe is quite nice, at least to a category theorist. First of all, what is De Finetti's theorem about? It's about exchangeable measures, or since we're doing category theory, exchangeable morphisms with an input. What does it mean, exchangeable? Okay, it's a morphism into the categorical product, which is invariant under finite permutation. So x to the n is an infinite product. You can permute finitely many of its factors, but unboundedly finitely many, okay? So it's not like a bijection of n in general, it's just permute a finite amount of factors, but like you don't have any limit on how big the amount of factor is. So that gives you a morphism from xn to xn. We're seeing that P makes this diagram commute, all right? So it's a group, it's an infinite group, countably infinite group, acting on the set, and P is an invariant morphism for this group action. That's a commutative diagram, a cone. So as category theorists, we might want to ask, what's the limit? All right, what does De Finetti theorem says? Well, in Borel stock, for every nx, there is a natural bijection between, De Finetti didn't say natural, but it is natural. Again, natural transformations didn't exist at the time. Natural bijection between cones like this, so exchangeable morphisms or exchangeable probability distributions, and maps into Px, so random morphisms into the space of probabilities, or if you want probabilities over probabilities, making this diagram commute. In other words, Px is the limit of this diagram. Px is the limit of these diagrams and permutation, and the universal map is given by copying infinitely many times and sample each component. So the limiting cone is exactly taking independent identically distributed samples. What's that? You have a coin and you keep sampling from it with the same coin, okay? The copy map is because it's the same coin, okay? That's what you do in statistics. So let me say this, why I like this so much. We're saying that, what is Px? What are probability distributions? Well, they are defined in terms of a universal property. This universal property, they represent the presheaf of cones over this diagram. In another way, probability distributions are the representing objects of exchangeable sequences. Okay? So probability distributions are exactly the same thing that you learn by looking at exchangeable processes. And how do you learn a probability distribution? Well, by taking repeatedly many samples. Now, if you're a frequentist, you take the statement on the nose. If you're Bayesian, well, you have a prior, and then you take all your samples and update it until you get the right one, right? But either way, what's going on here is it's telling you that probabilities are exactly the same thing that you learn by making experiments, repeated experiments. Probabilities can be distinguished that way, and there's nothing else, nothing more that you learn besides that. So this is kind of what you do in statistics or even in science, right? When you want to find out the law, these are the experiments that you make. Like the reason why, if in sense statistics work, is because probability measures are exactly learnable through IID samples. And this is stated very nicely in terms of universal property using Markov categories, okay? I'm not gonna go through the proof because, I mean, it's categorical, it's just string diagrams, but it's a little bit long. You can look at the paper. I want to conclude by giving you an example, okay? Because this looks abstract, like what does it mean that exchangeable IID samples, what does it mean? All right, so take a coin, heads or tails, flip it repeatedly, okay? And suppose that by flipping your coin, you see heads, 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 heads. What do you expect to see next? Now, you all know, at least each one in this room knows that friend that says that number hasn't come in the lottery for like years. It's time to bet on that one. Spoiler, it doesn't work. Also because, let's be scientists, right? Let's be scientists, and suppose that instead of a coin, it's a fish. We are biologists, and we're observing a fish if it preserves, if the fish prefers cold water or like lukewarm water. And suppose that this fish goes to like the warm water, and another fish of the same species, again, warm water, warm water, warm water. What do you expect the next member of the species to do, right? You don't say, now it's time for cold water. You think you're onto something. You think, oh, there's a paper here I can write. Like, I think I have found something about the distribution that these fish are following, okay? And so, if anything, we expect to see heads again. But there is an apparent paradox. How is it possible? Aren't these coin flips all independent? Like, these fish don't talk to one another. So how is it possible that we can make a prediction about the future knowing the past if all these events are independent? Like, you see the problem, right? And okay, so suppose we check our coin very carefully to see if it's like loaded, biased, if it has two heads. And we see that no, the coin is perfectly fine and fair. All right, then what do we expect? Well, 50-50. We were just very lucky to have this sequence of heads, right? Now we know. So what's going on here? If we don't know the coin, then there is correlation between the different coin flips. There is information that it's withholding from us. What information? What do all the coin flips have in common? Well, that it's the same coin, that each time it's following the same law. But once you know the coin, once you know what law it's following, then all the coin flips are independent. It's so the same coin. It's a little bit like before. Remember the coffee and pizza example. If you don't know where those people are from, you see some information about it. The fact that the pizza and the espresso are correlated has some information that's withholding from you. What? Well, where those people are from. But once you know that, then they're independent. Same thing here. So if P is generic but exchangeable, there's no reason why this should be splittable here. However, suppose that you know exactly the distribution of the coin, so that this mu becomes deterministic. Now remember from the exercises, first exercise session, deterministic things always split. So if you're sure about the coin, then this thing split, okay? So knowing the probability distribution is exactly what's going to make this conditionally independent, and that's exactly the thing that you can learn by making all these examples. And this is what De Finetti had in mind when he formulated his theorem, and I think using string diagrams and Markov categories can show this like very nicely, because it's really just about things that split or not, depending on whether they are deterministic. Okay? Any questions? Then, oh yes, there's one. Oh, this. Yes, P is the monad. So here we are in no. So this is the Markov category arising from a monad. A PX needs to be, if it exists, the right adjoint to the inclusion of deterministic morphisms into all morphisms. If there exists, then you can prove it's a probability monad. Or, I mean, one could go conversely, like if this limit exists, you can define P that way, right? And I mean, if the right things exist, yes. The nice thing is that this kind of gives you a definition of the objective probability measure, so by universal property. So you can reconstruct it. All right, so I'm going to stop here. These are some results. We didn't just do De Finetti using Markov categories. There's a lot more probability you can do with them. Here's a very incomplete list. There's a lot more we're doing. And if you want some references to get you started, here there are some more at the very end of the exercise sheet. So I'm 5 minutes over time, so let me stop here. Thank you for coming.